So in Calculus 3, you know how to take integrals, and now you can take integrals of vector valued functions. The way we define our integrals is you just do component-wise, like you would do derivatives. So if you see the notation, take the integral of this vector valued function, it really just means take the integral of each component. What you get is your answer. As an indefinite integral, when you take this integral, you'll have a function of t for this component when you're done, and a function of t for this component. It really is the antiderivative, and you have to remember to add individual constants. So there'll be a constant for this function and a constant for the g function. If you're talking about a definite integral, same notation, still doing it component-wise, so you still do it for just the x component, the y component. What you get is a constant for, or just some number, supposed to be the area underneath the curve, I guess, for the x component, the area underneath the curve for the y component, and so on. But that's just really going to be a vector that represents the total of each of the components. Its application depends on context. Whatever your vector valued function is supposed to be representing, you try to look in that context. What does the integral actually tell you? As an antiderivative, it just gives you a curve that you can draw. As a definite integral, it gives you, I don't know, the total vector, which maybe doesn't make sense unless you have a context that it can make sense in. We're asked to find the definite integral, which really just means take the integral of each of the individual components. So I find the antiderivatives using the same rules I'm used to for each of the different components. I evaluate the limits of my integration the same way I normally do, but just have two expressions I do that in. And I get a vector that somehow represents the total of all of the x component and the total of all of the y components separately.